Tonight, we're going to take a question that sounds simple, almost casual, and follow it all the way to the bottom. What would actually happen if you traveled 1 light year? Not what would it be like in the imaginary sense, not in the science fiction sense of stepping into a ship and emerging at a destination, but in the specific physical, biological, engineering, psychological, and astrophysical sense of what would genuinely occur if a human being attempted to cross a distance of 1 light year in a spacecraft of any design that current or near-future physics permits. The question sounds accessible because a light year is a familiar unit, something that appears on posters and documentaries and in casual astronomical conversations. You know that the nearest star is about 4 light years away and that distant galaxies are billions of light years across, and this familiarity makes a single light year sound like a modest, perhaps even reasonable, ambition. It is not. 1 light year is approximately 9.46 trillion kilometers. If you drove a car at highway speed continuously without stopping, it would take you approximately 11 million years to cover that distance. The Voyager 1 spacecraft, the fastest long-duration vehicle humanity has ever launched and currently the most distant artificial object from Earth, is moving at about 17 kilometers per second and has been traveling for nearly 50 years. It has covered roughly 0.002 light years. At its current speed, it would take Voyager approximately 73,000 years to travel 1 light year. Tonight's exploration is not an exercise in despair about human limitations. It is something more interesting, an examination of what the universe's physics actually requires of anything attempting such a journey, what the specific obstacles are and which ones are fundamental versus engineering challenges, what the experience would be like for any hypothetical traveler at any feasible speed, and what lies at the 1 light year destination that makes the question worth asking in the first place. The answers involve general and special relativity, nuclear physics, radiation biology, orbital mechanics, materials science, psychology, and astrophysics. They are simultaneously more difficult and more interesting than the casual framing of the question suggests, and they illuminate something important about both the nature of interstellar space and the nature of the physical laws that govern what can and cannot be done within it. By the end of tonight, you will understand not just why traveling 1 light year is hard, but precisely which aspects of it are hard, how hard they are quantitatively, which of the obstacles might eventually yield to technological progress, and which are fundamental features of physics that cannot be engineered around. You will also understand what 1 light year of distance actually means in terms of the physical environment, the astronomical objects, and the structure of the universe at that scale. If this kind of thorough, honest, physically complete investigation of a question everyone thinks they already understand is what you come here for, subscribe and leave a like. It genuinely helps reach more people who want real answers rather than comfortable approximations. Now, let us begin with what a light year actually is, because the definition itself contains the first surprise. The question also has a specific structure that makes it more productive than the more common framing of how long would it take to reach the nearest star. 1 light year is not defined by any star's location. It is a round number in a unit system based on the speed of light and the duration of a year, and asking what happens in crossing exactly 1 light year forces you to think about the journey itself rather than the destination. The nearest star at 4.24 light years is a destination with a specific character that shapes how people think about the challenge. 1 light year is just a distance, and the honest answer to what happens during crossing it must come from physics and engineering rather than from any attractive destination that might provide motivation for the effort. There is also something revealing in the disconnect between how light years sound and what they mean. The universe uses light years as a natural unit, but the universe did not design human beings to have any intuition about them. A light year sounds like a manageable distance, the way $1 trillion sounds like a large number but not an incomprehensible one. Both impressions are misleading. The actual content of 1 light year of distance, the time it would take, the energy it would require, the hazards it would involve, the effect it would have on a human traveler, is staggering in ways that the familiar units obscure. This is the kind of question that rewards following to the bottom. Not because the bottom is reassuring, but because knowing what is actually there, knowing precisely how hard the problem is and in what specific ways it is hard, is more useful than either optimistic vagueness or pessimistic dismissal. A light year is not a unit of time. This sounds obvious, but its implications are less obvious than they appear. A light year is the distance that light travels through a vacuum in exactly 1 Julian year, defined as 365.25 days of 86,400 seconds each. The speed of light in vacuum is exactly 299,792,458 meters per second by definition, since the meter is now defined in terms of this speed. Multiplying by the number of seconds in a Julian year gives 9,460,730,472,580,800 meters, or approximately 9.461 times 10 to the 15th meters, or about 9.461 trillion kilometers. The unit exists because it is convenient for describing astronomical distances, which in the natural units of meters or even kilometers involve such large numbers that they become practically meaningless to intuition. Saying Proxima Centauri is 4.24 light-years away is more useful than saying it is 40.1 trillion kilometers away, because the number 40.1 trillion is no more intuitive than 4.24. But the light-year as a unit carries within its definition a crucial physical fact. The speed of light is the fastest possible speed for any material object or information-carrying signal, and even at that maximum speed, 1 light-year takes exactly 1 year to cross. No technology can make a light-year shorter. No engine can decrease the distance. The light-year is a hard physical quantity that no engineering can alter. The light-year also defines a communication limit. If you are 1 light-year from Earth, any message you send takes 1 year to arrive at Earth. Any response takes another year to return. You are operating with a 2-year communication round trip, minimum, permanently, inescapably. This is not a function of radio technology or transmission power. It is a function of the finite speed of light, which is the finite speed of all electromagnetic signals including radio, light, and any other wavelength. Understanding the physical scale of a light-year requires comparison to familiar distances. The distance from Earth to the Moon is approximately 384,400 kilometers. The distance from Earth to the Sun is approximately 149.6 million kilometers, defined as 1 astronomical unit. 1 light-year is approximately 63,241 astronomical units. The Sun is about 8.3 light-minutes from Earth. Pluto at its farthest is about 7.5 light-hours. The Voyager 1 spacecraft is currently about 22.5 light-hours from Earth. 1 light-year is about 40,000 times farther than Voyager 1's current position. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. The center of the Milky Way galaxy is about 26,000 light-years away. The Andromeda galaxy is approximately 2.5 million light-years away. These comparisons establish that 1 light-year is not a cosmological distance. It is not even an interstellar distance in the sense of reaching another star. 1 light-year places you firmly in the outer reaches of our own solar system, perhaps within the Oort Cloud, the vast spherical shell of icy bodies that surrounds the solar system at distances of roughly 2,000 to 100,000 astronomical units. You would not have reached another star. You would barely have left your own. The light-year also has an interesting relationship to human timescales. 1 Julian year is approximately the time required for Earth to complete 1 orbit around the Sun, a duration calibrated to the agricultural cycle and the seasons, which are features of the particular planet we live on. There is nothing cosmically significant about the year as a time unit, and yet the distance that light covers in exactly this biologically meaningful unit turns out to be a quantity that separates stars from each other. Most stars in the Milky Way are separated from their nearest neighbors by distances of 1 to 10 light-years. This coincidence, that the light-year is both a convenient human unit and a meaningful astrophysical scale for stellar separations, is a coincidence. It says nothing deep about the universe. But it does mean that when astronomers use light-years to describe interstellar distances, they are using a unit that gives numbers between 1 and 10 for most stellar separations, which is cognitively convenient even if physically arbitrary. The relationship between light-years and the travel time of currently achievable spacecraft is perhaps the most illuminating single fact for calibrating the difficulty of interstellar travel. Voyager 1's 47-year journey of 0.002 light-years means that scaling to 1 full light-year requires multiplying the journey by 500. That would be 23,500 years of travel, roughly the time since the end of the last ice age, when humans were still in the Stone Age and no writing had yet been invented. The distance implied by a single light-year is, in terms of current technology, not just difficult. It is in a different category from any challenge humanity has previously attempted. The best way to establish what actually traveling 1 light-year would require is to begin with what has actually been done, and then to scale from there. Humanity has launched exactly 5 spacecraft that are on trajectories that will eventually take them out of the solar system. Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and the New Horizons probe. Of these, Voyager 1 is the current record holder for distance from Earth. Voyager 1 was launched on September 5, 1977. As of 2024, It has been traveling for nearly 47 years and is approximately 23.8 billion kilometers from Earth, or roughly 22.5 light-hours. Its current velocity relative to the Sun is approximately 17 kilometers per second, or about 61,200 kilometers per hour. This is fast by any terrestrial standard. At this speed, you could circumnavigate Earth's equator in about 40 minutes. But 17 kilometers per second is approximately 0.0057% of the speed of light. At Voyager 1's current speed, traveling 1 light-year would require approximately 17,500 years. This is longer than recorded human history. It is longer than the period since the end of the last ice age. It is longer than any human civilization has existed. The entire agricultural revolution, the development of writing, the rise and fall of every empire in history, and everything that has happened since would fit multiple times into the travel duration. Voyager 1 was not designed for interstellar travel. It was designed to study the outer solar system, and its trajectory to the outer planets was the highest priority. Its speed at launch was determined by the requirements of the Jupiter and Saturn flyby missions, not by any desire to maximize velocity for an interstellar journey. If the designers had wanted to maximize velocity for interstellar transit, they would have done things differently, though the fundamental constraint would have been the same. Rocket propulsion is extraordinarily expensive in terms of fuel mass required per unit of velocity achieved. The New Horizons spacecraft, launched in 2006 and currently about 55 astronomical units from Earth, had a somewhat higher initial velocity than Voyager due to improvements in launcher technology, reaching approximately 16.26 kilometers per second at launch. It is moving somewhat faster than Voyager in the direction away from the Sun due to its trajectory, but will not surpass Voyager in total distance for many decades. The fundamental point is that after nearly 50 years of operation with the best rocket technology of two different eras, humanity's fastest spacecraft have covered about 22.5 light-hours out of the 63,241 astronomical units, or about 8,760 light-hours, that constitute a single light-year. The Parker Solar Probe provides an interesting contrast with Voyager 1 in terms of speed. Parker is not on an escape trajectory from the solar system. It is in a highly elliptical solar orbit that brings it extremely close to the Sun, and its maximum speed of approximately 192 kilometers per second, achieved during its closest solar passes, is the fastest speed any human-made object has ever reached. This is about 11 times Voyager's current speed. But even at 192 kilometers per second, the time to travel 1 light-year would be approximately 1,560 years. Parker's high speed is achieved by falling toward the Sun's gravity well and is not maintained. It decelerates as it moves back out from perihelion. The distinction between instantaneous speed and sustained transit velocity is critical for interstellar travel assessment. A spacecraft that achieves a high speed at one point in its orbit but cannot maintain it does not benefit the interstellar travel calculation. What matters is the speed maintained during the transit, which for any plausible propulsion system is determined by the total energy available, the efficiency of converting that energy to kinetic energy, and the mass of the spacecraft. New Horizons passed Pluto in July 2015 at approximately 14 kilometers per second relative to the Sun, and it remains the third fastest solar escape trajectory after the two Voyagers. After its Pluto flyby, New Horizons has been traveling through the Kuiper Belt and is currently at roughly 57 astronomical units from the Sun, about a quarter of Voyager 1's distance despite being almost 30 years newer. The age of the spacecraft, not the launch date, is what determines distance for constant velocity interstellar trajectories. Scaling Voyager's speed to more intuitive units reveals the fundamental nature of the problem. Voyager 1 travels at about 3.6 astronomical units per year. 1 light-year is 63,241 astronomical units. Voyager therefore covers a full light-year's worth of distance in approximately 63,241 divided by 3.6, or approximately 17,567 years of continuous flight. To be in the same ballpark as a meaningful interstellar transit, we need spacecraft velocities not 10% faster than Voyager or even 10 times faster, but on the order of 10,000 to 100,000 times faster. The gap between current best and what is needed is not incremental but categorical. The Tsiolkovsky rocket equation, derived by Konstantin Tsiolkovsky in 1903, describes the relationship between a rocket's change in velocity, its exhaust velocity, and the ratio of its initial mass to its final mass. The equation is simple to write and devastating in its implications. Delta V equals exhaust velocity times the natural logarithm of the initial mass divided by the final mass. The specific implication that makes interstellar rocket travel almost prohibitively difficult is the exponential relationship between the required mass ratio and the desired velocity change. For a given exhaust velocity, doubling the desired delta V does not double the mass ratio, it squares it. Tripling the desired delta V cubes the mass ratio. The relationship between ambition and fuel requirement is exponential. For chemical rockets, the exhaust velocity is typically in the range of 2.5 to 4.5 km per second for the most energetic propellant combinations. To accelerate a 1 kg payload to 100 km per second using a chemical rocket with an exhaust velocity of 4.5 km per second, the initial mass would need to be roughly e to the power of 100/4.5, or e to the 22nd power, which is approximately 38 billion kilograms. This is roughly 6 times the mass of Earth, of which essentially all is propellant and essentially none is payload. 100 km per second is still only about 0.033% of the speed of light, and 1 light-year would still require roughly 94,000 years to cross at that speed. Even nuclear thermal rockets, which heat a propellant by passing it through a nuclear reactor and can achieve exhaust velocities of perhaps 8 to 10 km per second, improve the situation but do not fundamentally change it. The exponential character of the rocket equation means that even doubling the exhaust velocity cuts the required mass ratio roughly to its square root rather than halving it, which sounds like improvement but still leaves the mass ratios for meaningful interstellar travel in the range of trillions to 1 for even modest fractions of the speed of light. Nuclear pulse propulsion, in which a spacecraft is driven forward by the detonation of nuclear bombs behind it, can in principle achieve exhaust velocities of thousands to tens of thousands of kilometers per second, radically changing the mass ratio equation. The Orion concept studied by the US government in the late 1950s and early 1960s proposed using fission bombs, with exhaust velocities around 10,000 kilometers per second, potentially achievable. Project Daedalus, a detailed engineering study conducted by the British Interplanetary Society in the 1970s, proposed using inertial confinement fusion of deuterium helium-3 pellets to achieve exhaust velocities of roughly 30,000 kilometers per second. Even at this exhaust velocity, reaching 10% of the speed of light would require a mass ratio of approximately 5 to 1. But the rocket equation never disappears. Whatever the propulsion method, if the reaction mass has to be carried along for the journey, the exponential relationship between velocity and required initial mass imposes a brutal tax on every additional fraction of light speed achieved. The paradox embedded in the rocket equation is that the only way to avoid it is to not carry the fuel, which means the fuel must somehow be provided by something other than the spacecraft itself. This is the conceptual foundation of several proposed interstellar propulsion concepts. The ramjet concept proposes collecting interstellar hydrogen as fuel, the laser sail concept proposes having the energy source remain at the launch point, and the beamed power concept proposes transmitting energy to the spacecraft from Earth or from an intermediate energy relay. Each of these concepts eliminates some aspect of the fuel mass penalty but introduces its own challenges. The rocket equation also has an important implication for deceleration that is worth stating explicitly. If you accelerate to a velocity using a rocket, and you want to decelerate to rest at your destination, and you carry the fuel for deceleration with you, then the fuel you carry for deceleration must itself be accelerated to your travel velocity during the acceleration phase. This means the fuel required for the complete mission of accelerate cruise decelerate is dramatically larger than the fuel required for acceleration alone. For a fusion rocket with an exhaust velocity 10 times the cruise velocity divided by 10, the mass ratio for a round trip including deceleration would be approximately 100, meaning 99% of the initial launch mass is propellant. The fact that the rocket equation has this specific mathematical form, that the required mass ratio is an exponential function of the velocity to exhaust velocity ratio, is a consequence of basic Newtonian mechanics and cannot be avoided for any reaction propulsion system. It is not a result of any particular engineering inefficiency or technological limitation. It is a consequence of conservation of momentum. The popular conception of space between the stars is one of absolute emptiness, a perfect vacuum so complete that nothing exists in it. The actual interstellar medium contradicts this picture in ways that are both scientifically important and physically consequential for any spacecraft attempting to traverse it. The local interstellar medium, the region within a few hundred light-years of the Sun, is far from empty. It consists of gas, primarily hydrogen and helium, dust particles, cosmic rays and magnetic fields, all in a complex, structured state that varies significantly with position. The average density of the interstellar medium in the local region is roughly 1 atom per cubic centimeter, compared to about 10 to the 19th atoms per cubic centimeter in Earth's atmosphere at sea level. This is genuinely very sparse by any ordinary standard. But the phrase 1 atom per cubic centimeter describes an average that disguises enormous local variation. The interstellar medium is organized into distinct phases: hot, diffuse regions where the gas has been heated and ionized by nearby supernova remnants and stellar winds, warm regions of neutral and ionized gas at intermediate temperatures and densities, and cold, dense molecular clouds where hydrogen exists in molecular form and stellar formation occurs. The solar system is currently moving through a region called the local bubble, a cavity in the interstellar medium that was cleared by supernovae roughly 10 to 20 million years ago and is filled with hot, very low-density gas. The boundary between the heliosphere, the region of space dominated by the solar wind and the sun's magnetic field, and the interstellar medium proper is called the heliopause. Voyager 1 crossed the heliopause in 2012 at a distance of roughly 121 astronomical units. Beyond the heliopause, the interstellar medium begins in its proper sense. Even in the hot, sparse local bubble, there are gas molecules that would interact with any spacecraft moving at high velocity. At low velocities, this gas is essentially irrelevant. At velocities approaching a significant fraction of the speed of light, even a single hydrogen atom encountered by the spacecraft's structure has a kinetic energy in the spacecraft's rest frame that is equivalent to a high-energy cosmic ray. The interaction between a high-velocity spacecraft and the interstellar medium is not a matter of occasional encounters with an essentially empty space. It is a matter of continuous bombardment by projectiles whose energy in the spacecraft frame scales with the square of the spacecraft velocity. The solar system currently sits inside a specific named feature of the local interstellar medium called the local interstellar cloud, also called the local fluff, a clump of warm gas roughly 30 light-years across with a density somewhat higher than the rest of the local bubble. The Sun entered the local interstellar cloud between 44,000 and 150,000 years ago, based on measurements of the cloud's properties. The Sun may be near the edge of this cloud, and within a few thousand to tens of thousands of years the solar system may exit into the hotter, less dense general environment of the local bubble. The temperature of the interstellar gas in the local interstellar cloud is approximately 6,000 Kelvin, comparable to the surface temperature of the Sun. But this is the kinetic temperature of the individual particles, meaning the average kinetic energy of each particle corresponds to this temperature, not that the gas would burn you if you touched it. The density is so low that the actual energy flux from the hot gas is negligible compared to the energy flux from the Sun or from cosmic radiation. Thermodynamic temperature and thermal energy density are very different things at these low densities. For a spacecraft, the interstellar medium beyond the heliopause represents a fundamental change in environment. Inside the heliosphere, the solar wind sweeps charged particles and clears much of the gas and dust that would otherwise be present. Outside, the spacecraft encounters the raw interstellar medium in its natural state, the gas, dust, magnetic fields and cosmic ray environment that permeates the space between stars. The spacecraft's interaction with this environment at any significant fraction of light speed would be qualitatively different from its interaction at low speed. The warm ionized medium component of the interstellar medium, which constitutes roughly 20 to 30% of the ISM by volume, has an electron density of roughly 0.03 per cubic centimeter and a temperature of about 8,000 Kelvin. The warm neutral medium, similarly distributed in volume, has a hydrogen density of roughly 0.5 atoms per cubic centimeter and a temperature of 6,000 to 10,000 Kelvin. The cold neutral medium, concentrated in sheets and filaments, has densities of 20 to 50 atoms per cubic centimeter and temperatures of 50 to 100 Kelvin. A spacecraft transiting the solar neighborhood would pass through regions dominated by different ISM phases depending on its specific trajectory, and the radiation and particle environment would vary accordingly. Interstellar space is permeated by radiation in forms that range from merely hazardous to immediately lethal for unprotected biological matter. Understanding the radiation environment between stars is essential for assessing the feasibility of human interstellar travel at any speed. The first category of interstellar radiation is galactic cosmic rays, charged particles, primarily protons and helium nuclei, accelerated to enormous energies by supernovae and other high-energy astrophysical processes and then distributed throughout the galaxy by its magnetic fields. Within the heliosphere, the solar wind and the Sun's magnetic field partially deflect these cosmic rays, providing some shielding to the inner solar system. Beyond the heliopause, cosmic ray fluxes are higher and the protective shielding of the solar wind is absent. The annual radiation dose from galactic cosmic rays in interstellar space is roughly equivalent to several hundred millisieverts per year, compared to Earth's average natural background of about 3 millisieverts per year. This is elevated but not immediately lethal, though it would significantly increase cancer risk over a multi-decade voyage and could eventually be incapacitating. The most energetic cosmic ray particles, at energies above roughly 1 GeV per nucleon, penetrate essentially any practical shielding material and cannot be blocked by adding mass to a spacecraft's hull. The shielding would need to be measured in meters of lead to reduce cosmic ray exposure to Earth-equivalent levels, which is not feasible for any spacecraft. The second radiation hazard specific to high-velocity travel is the transformation of the interstellar medium from a sparse gas into an energetic radiation field. A spacecraft moving at 10% of the speed of light would encounter hydrogen atoms at a relative energy equivalent to kinetic energies of roughly 4.7 million electron volts per proton, placing them in the regime of energetic nuclear particles. The flux of these encounters at the average interstellar density of 1 atom per cubic centimeter and a velocity of 0.1 c would produce a radiation dose on the spacecraft's forward-facing surfaces of roughly 10 gigaelectronvolts per square centimeter per second, which is an extraordinarily high radiation environment by any terrestrial standard. At half the speed of light, the energies of individual hydrogen impacts on the spacecraft's forward shield would be in the hundreds of millions of electron volts per nucleon, deep in the regime of spallation-inducing nuclear interactions. The shield would experience nuclear reactions as hydrogen nuclei struck it at these energies, producing secondary particles including neutrons that would penetrate the shield and irradiate the crew behind it. Managing this forward-facing radiation problem is one of the primary engineering challenges of any high-speed interstellar mission. Solar energetic particles, protons and heavier nuclei accelerated by solar flares and coronal mass ejections to energies of tens to hundreds of megaelectronvolts, represent an additional radiation hazard in the inner solar system. These events can deliver substantial radiation doses to astronauts in deep space on short timescales, sometimes within hours of the solar event. Shielding against solar energetic particles is more tractable than shielding against galactic cosmic rays because they have lower energies and can be attenuated by modest mass. As a spacecraft moves away from the Sun, these solar energetic particle events become less significant because the particle flux decreases with distance, and beyond the heliopause they cease to be relevant. The dominant radiation hazard in interstellar space is therefore galactic cosmic rays, which have a broad spectrum of energies extending from hundreds of megaelectronvolts to tens of joules per particle in the most extreme cases, the ultra-high-energy cosmic rays. The GCR flux is essentially constant throughout interstellar space, modulated slightly by the solar cycle near the Sun but essentially invariant at interstellar distances. The dose rate from GCRs in interstellar space, roughly 400 to 600 millisieverts per year depending on the particle environment, is far above the radiation dose limits specified for occupational exposure of radiation workers on Earth of 20 millisieverts per year. NASA's current exploration mission limit for lifetime radiation exposure is approximately 600 millisieverts for low Earth orbit operations, intended to limit the career excess cancer risk to no more than 3%. A multi-decade interstellar transit with GCR exposure of 400 to 600 millisieverts per year would deliver lifetime doses many times this limit even without any contribution from the velocity-dependent forward radiation environment. The shielding challenge for galactic cosmic rays is categorically different from the shielding challenge for solar energetic particles. Solar particles have energies in the tens to hundreds of megaelectronvolts and are largely stopped by a few grams per square centimeter of material, meaning a few centimeters of aluminum or similar shielding substantially reduces exposure. Galactic cosmic rays at their characteristic energies of 1 to 10 gigaelectronvolts per nucleon require shielding masses of tens of grams per square centimeter to reduce the dose by even a factor of 2, meaning tens of centimeters of aluminum or water equivalent. A complete habitat with enough water or polyethylene shielding to reduce GCR dose to occupational limits would require a mass of shielding comparable to or exceeding the rest of the spacecraft, making it impractical for any propulsion system required to accelerate the mass to interstellar velocities. Interstellar dust represents a distinct and in some ways more immediately damaging hazard than gas, because dust particles are larger and therefore carry more kinetic energy per impact at high velocities. At high enough velocities, even microscopic dust particles become effectively explosive. Interstellar dust consists of solid particles ranging from roughly a few nanometers to a few micrometers in diameter, composed primarily of silicates, carbonaceous material, and ices in various combinations. The size distribution is steeply weighted toward the smaller end. There are many more nanometer scale grains than micrometer scale ones. The number density of dust particles in the local interstellar medium is much lower than the gas density, roughly 1 dust particle per million cubic kilometers for micrometer scale grains, but the kinetic energy carried by each particle at high velocity is correspondingly higher than for individual gas atoms. A dust grain 1 micrometer in diameter with a density of roughly 2,500 kilograms per cubic meter has a mass of approximately 1.3 times 10 to the minus 15 kilograms. At a spacecraft velocity of 10% of light speed, this grain has a kinetic energy in the spacecraft's rest frame of roughly 5.8 gigajoules, equivalent to about 1.4 tons of TNT explosive. At half the speed of light, the relativistic kinetic energy would be substantially larger still. A single micrometer scale dust grain would release this energy instantly into whatever material it struck first, excavating a crater and sending shock waves and ejecta into the structure. The forward-facing surface of any high-velocity spacecraft would therefore need to be treated as a shield against hypervelocity impacts rather than just a structural surface. This is not a new concept. Spacecraft in the inner solar system require Whipple shields against micrometeorite impacts, and the principle is the same but at much higher energy. The challenge for interstellar velocities is that the energies involved are so much larger that no conventional shield design can absorb them. The material strength is irrelevant at these energies, and the shield must instead be designed to ablate and vaporize the impacting particles rather than to structurally resist them. The Project Daedalus study estimated that a beryllium shield roughly 4 mm thick could protect against the interstellar dust environment for a journey to Barnard's star, the nearest star system after Alpha Centauri, at approximately 12% of the speed of light. The Breakthrough Starshot project, which proposes sending gram-scale laser-sail spacecraft to Alpha Centauri at 20% of light speed, has specifically identified interstellar dust as a critical challenge requiring erosion-resistant forward coatings. The mass removed from the forward surface by dust impacts over a several-decade journey would be comparable to the initial shield mass for some realistic interstellar dust size distributions. The size distribution of interstellar dust grains follows a power law with the number of grains increasing steeply towards smaller sizes. Most interstellar dust grains are nanometer scale, and their kinetic energies at high spacecraft velocities, while individually smaller than for micrometer scale grains, are collectively significant because of their much higher number density. At 10% of the speed of light, a nanometer scale grain with a mass of roughly 10 to the minus 24 kilograms carries a kinetic energy of about 5,000 electron volts, far below the binding energies of bulk materials and causing primarily electronic excitation and chemical changes in the target material rather than macroscopic cratering. However, the nanometer grains are so numerous that over a multi-decade journey, the cumulative sputtering they cause on the forward surface can remove significant material. Studies for the Breakthrough Starshot mission have estimated that a centimeter-scale laser sail chip traveling at 20% of light speed would lose several grams of material from its leading surface due to dust impacts over a 4-light-year journey. For a larger spacecraft carrying humans, the forward shield would need to be made of hard, erosion-resistant material and designed to be replaced or resupplied if the journey is long. The fact that the Breakthrough Starshot project has identified interstellar dust as a critical challenge requiring specific material solutions, for a spacecraft the size of a postage stamp traveling for only 4 years, gives some indication of how severe the problem would be for any larger crewed mission over a longer timescale. The dust problem is not insurmountable. Erosion-resistant materials like diamond or beryllium can withstand high fluences of energetic particles, and layered shield designs can manage the cratering from larger grains. But it requires engineering solutions that have not yet been demonstrated at any relevant scale. If the propulsion problem could somehow be solved and a spacecraft could accelerate to a substantial fraction of the speed of light, the physics of special relativity would transform the experience of the journey in ways that are both mind-bending and mathematically precise. Time dilation, the slowing of time for moving objects relative to stationary observers, is the most important of these effects for understanding what would actually happen to a hypothetical traveler. The Lorentz factor, gamma, equals 1 divided by the square root of 1 minus the square of velocity divided by the square of the speed of light. At low velocities, gamma is essentially 1 and relativistic effects are negligible. As velocity approaches the speed of light, gamma grows without bound. At 90% of light speed, gamma is approximately 2.29, meaning the traveler experiences about 2.29 times less time than Earth-based observers. At 99%, gamma is about 7.09. At 99.9%, gamma is approximately 22.4. For a 1 light-year journey, the implications are direct. If a spacecraft traveled at 90% of light speed, it would cover 1 light-year in approximately 1.11 years of Earth time but only about 5.8 months of the traveler's proper time. At 99% of light speed, Earth time would be about 1.01 years for the journey and the traveler would experience about 52 days. At 99.9%, the traveler's experience would compress to about 16 days. These numbers illustrate both the appeal and the limitation of relativistic travel. The appeal is that extremely high velocities allow a traveler to cover enormous distances in a subjectively short time. A traveler at 99.99% of light speed could reach 1,000 light-years away and experience only a few years of travel time, though 1,000 years would have passed on Earth. The limitation is that the 1 light-year case does not dramatically compress the journey time. Even at 90% of light speed, the traveler experiences more than half a year of travel, and the trip is not dramatically shorter subjectively than for the people watching from Earth. The distinction between proper time and coordinate time becomes critically important for communication and return journeys. If a traveler leaves Earth at 90% of light speed toward a destination 1 light-year away, the journey takes 1.11 years of Earth time. If they then turn around and return immediately, Earth time elapsed is 2.22 years while the traveler has experienced about 1.16 years. This is the twin paradox in its simplest form. The traveler returns younger than a twin who stayed on Earth, because the traveler's clock genuinely ran slower during the high-velocity portions of the journey. The twin paradox, while often presented as a paradox, has a completely unambiguous resolution in special relativity that is worth stating carefully because it illuminates the physical reality of time dilation. When the traveling twin returns to Earth, they genuinely are younger than the twin who remained, in the sense that their biological clock has accumulated less time. This is not an illusion or a perception. The difference in age is physically real and would be confirmed by any measurement. The reason this is not actually paradoxical is that the two twin situations are not symmetric. Special relativity's time dilation is symmetric for two observers in uniform relative motion, but the traveling twin must decelerate and accelerate to turn around and return. These acceleration phases break the symmetry. The traveling twin is not in an inertial reference frame throughout the journey, while the Earth-based twin is. The acceleration phases cause the traveling twin to age less than the Earth-based twin by an amount determined by the velocity profile of the journey, and this difference is not a matter of perspective but a physical, observer-independent fact. For a 1 light-year journey at 90% of the speed of light with a turning-around component, the Earth-based twin ages about 2.23 years while the traveling twin ages about 1.16 years, a difference of about 1.07 years. At 99% of light speed, Earth ages 2.02 years while the traveler ages about 0.28 years, a difference of 1.74 years. The traveler genuinely returns about a year and 3/4 younger than they would have been if they had stayed home. This is a consequence not of perception or measurement artifacts but of the actual geometry of spacetime. The visual experience of traveling at near light speed would be profoundly alien, shaped by 3 relativistic optical effects that have no counterpart in everyday experience: relativistic aberration, the Doppler shift of light, and the headlight effect. Understanding these effects gives a concrete picture of the sensory environment that any relativistic traveler would inhabit. Relativistic aberration refers to the apparent change in direction of incoming light as a consequence of the observer's motion. A stationary observer sees photons arriving from all directions with an isotropic distribution if the sources are distributed uniformly. An observer moving at high velocity sees photons concentrated in the forward direction, as if the starfield were being swept toward the direction of travel. At 50% of the speed of light, stars that would appear uniformly distributed across the sky to a stationary observer now appear concentrated into a forward hemisphere, with the density increasing toward the direction of motion. At 90% of light speed, the majority of the visible starfield is compressed into a cone of about 36 degrees half angle centered on the direction of travel. At 99%, this cone narrows to about 8 degrees. The Doppler effect shifts the frequency of light received from ahead and behind. Stars and other light sources ahead of the spacecraft appear blue-shifted, their light received at higher frequency than emitted. Infrared sources ahead become visible light. Visible light ahead becomes ultraviolet or X-ray. Stars behind the spacecraft appear red-shifted. Visible light becomes infrared and eventually radio waves. At 10% of light speed, the blue shift ahead is about 10%. At 50%, the blue shift factor is approximately 1.73. At 90%, blue shift ahead produces a factor of about 4.4 in frequency increase. The practical consequence of extreme blue shifting is that the radiation environment ahead of a near-light-speed spacecraft includes X-rays and gamma rays from what would normally be soft ultraviolet or optical sources. The cosmic microwave background, which normally peaks in the microwave band, would be blue shifted into hard X-rays or gamma rays at velocities approaching the speed of light. The forward-facing surfaces and sensors of a relativistic spacecraft would need to be shielded against this transformed radiation environment in addition to the particle bombardment from the interstellar medium. The headlight effect combines aberration and Doppler shifts to concentrate both the direction and energy of incoming radiation into the forward direction. A traveler looking forward sees an intensely bright, blue-white region of sky containing essentially all the stars of the visible universe, compressed into a small cone. Looking backward, the sky appears nearly dark, with a few remaining redshifted sources dimly visible. The experience would be like traveling through a universe in which all the light in existence has been squeezed into the direction you are heading. The apparent dimming and brightening of stars as a function of their direction relative to the spacecraft's motion is another dramatic relativistic optical effect. Stars ahead of the spacecraft are brightened because the light is not only blue-shifted in frequency but also received at a higher rate. The photons are, in effect, caught up with faster by the moving spacecraft than they would be if the spacecraft were stationary. Stars behind are dimmed both by redshift and by the reduced photon collection rate. The combined intensity effect produces a brightening of stars ahead by the fourth power of the Doppler factor, and dimming behind by the same factor. At 90% of light speed, the Doppler factor for the forward direction is about 4.4, meaning stars directly ahead are amplified in intensity by roughly 4.4 to the fourth power, or about 375 times their apparent intensity to a stationary observer. They are also blue-shifted in frequency by 4.4. The combination makes the forward region of sky extraordinarily bright, with all the stars of the entire visible universe concentrated there and amplified by factors of hundreds. Looking back, everything is dimmed by the same factor, making the entire backward hemisphere nearly dark. The practical implications for a spacecraft with windows include designing the forward-facing windows or optical sensors to handle extraordinarily intense blue-shifted radiation without transmitting it to the crew. At high enough velocities, the optical and ultraviolet enhancement of the forward radiation would require the crew to be shielded from it rather than able to view it directly. The visual experience of near-light-speed travel, while dramatic, would need to be experienced through heavily filtered instruments rather than direct observation. The phenomenon of time of arrival compression creates another visual effect not commonly discussed. When a spacecraft is moving toward a source of light, the successive wave crests of the light arrive at shorter time intervals because each successive crest has a shorter distance to travel than the previous one. This is the relativistic Doppler effect, but it has a visual consequence beyond frequency shifting. Events at the source appear to occur faster than they actually do in the source's rest frame. A process taking 1 year at a destination star, viewed by a spacecraft approaching at 90% of light speed, appears to occur in about 1.1 months because the light carrying news of later events in the process arrives sooner than the light would take in the absence of the spacecraft's motion. This is the relativistic beaming of temporal information as well as spatial information. At 1 light-year from Earth, any communication involves a 1-year one-way delay. A question asked of the traveler takes 1 year to arrive, the response takes another year to return. From the moment the communication begins to the moment it concludes is a minimum of 2 years, with no possibility of shortening this through any technical means because the limitation is the speed of light itself rather than any particular technology. For practical mission operations, this communication delay transforms every interaction between the spacecraft and Earth from a conversation into a letter exchange measured in years. Mission controllers on Earth who detect a problem with the spacecraft cannot advise corrective action and receive confirmation that the action was taken in less than 2 years. Any emergency that develops at the spacecraft must be resolved entirely by the onboard crew independently, because help or guidance from Earth cannot arrive in time to be relevant. At lower velocities, the communication delay grows proportionally with distance traveled. A spacecraft moving at 17 kilometers per second, Voyager's current speed, would be at approximately 0.001 light-years after 17 years and would have a communication delay of about 8.8 hours, comparable to Voyager's current delay. After 1,000 years, the spacecraft would be at roughly 0.05 light-years and the delay would be about 18 days. After 10,000 years, at 0.5 light-years, the delay would be about half a year. The full 1-year delay at 1 light-year would not be reached for about 17,000 years at Voyager's speed. There is also a signal strength problem. Radio signals, like all electromagnetic radiation, decrease in intensity as the inverse square of distance. A signal that is easily received at 1 astronomical unit requires a transmitter 100 times more powerful to achieve the same received signal strength at 10 astronomical units, and 10,000 times more powerful at 100 astronomical units. At 1 light-year, approximately 63,241 astronomical units, the required transmitter power for an equivalent signal would be roughly 4 billion times greater than at 1 astronomical unit. Voyager's transmitter radiates at about 22 watts, and its 3.7-meter dish, combined with Earth's 70-meter deep space network antennas, barely provides sufficient signal margin at current distances. A spacecraft at 1 light-year with equivalent equipment would produce a signal effectively undetectable by any current or near-future Earth infrastructure. The deep space network sensitivity is not remotely adequate for interstellar communication at light-year scales. The signal strength problem requires quantitative treatment to appreciate its severity. The free space path loss formula, which describes how a radio signal's power decreases with distance, gives the fraction of transmitted power received at distance d for a transmitting and receiving antenna combination with specific gains. For the 70-meter deep space network antennas and a 2-watt transmitter at 1 astronomical unit, the received signal is easily manageable. At 1 light-year, 63,241 astronomical units, the signal power at the receiver would be weaker by a factor of 63,241 squared, roughly 4 billion, compared to the 1 astronomical unit case. To maintain the same received signal strength at 1 light-year that the deep space network currently achieves with Voyager at 22.5 billion kilometers, the transmitter power would need to be approximately 4 million times stronger, or the antenna areas would need to be 4 million times larger, or some combination of these. A 70-meter dish antenna at 1 light-year would need a transmitter of about 1 million watts rather than Voyager's 22 watts, and even this would be received at the same sensitivity by a 70-meter antenna on Earth. The 1 million watt transmitter requirement at 1 light-year is not insurmountable for a spacecraft with adequate power generation, but it illustrates the qualitative difference between solar system communication, which is manageable with current technology, and interstellar communication, which requires either enormously more powerful transmitters, enormously larger antennas, or more efficient communication protocols. The communication delay and signal strength together define the communication environment of interstellar space in a way that has no solar system analog. The navigation of a spacecraft through interstellar space presents challenges that are entirely unlike those of solar system navigation. Within the solar system, a spacecraft's position can be determined by very long baseline interferometry of radio signals, tracking the time delay and Doppler shift of radio communications between the spacecraft and multiple tracking stations on Earth. This technique achieves positional accuracy of a few meters at Voyager's distance of about 22.5 billion kilometers, an extraordinary precision. At 1 light-year, the 1-year communication delay makes real-time tracking impossible. Any positional measurement requires sending a signal to the spacecraft and waiting for a return signal, a process that takes a minimum of 2 years from initiation to result. By the time a positional fix is established, the spacecraft has moved significantly from the measured position, and the correction required to maintain the planned trajectory must be calculated from a position that is already 2 years old. Autonomous navigation, in which the spacecraft determines its own position and trajectory without dependence on Earth, becomes essential at interstellar distances. The technique of stellar navigation, determining position from precise measurements of the angles between multiple stars and the directions to known pulsars, can provide positional accuracy of roughly a few kilometers anywhere in the galaxy with appropriate instruments, but requires sophisticated onboard computation and precise onboard attitude control. The measurement of proper motion, the angular drift of nearby stars against the background of more distant ones, provides another navigational tool. As a spacecraft moves away from the solar system, the apparent positions of nearby stars shift in predictable ways determined by the baseline of observation. Tracking these shifts allows the spacecraft to verify its position and velocity. However, the precision required is extreme. At 1 light-year, a positional error of 1 astronomical unit, a tiny fraction of the total journey, corresponds to an angular error from Earth of about 1 arcsecond, which is at the limit of what current astrometry can achieve. Mid-course corrections for a hypothetical interstellar spacecraft are not free. Every velocity change requires propellant, and propellant is the most precious resource on any rocket-powered spacecraft. Navigation errors that require significant correction burns can compromise the entire mission by consuming propellant budgeted for deceleration at the destination. The specific challenge of navigating to a precise target, a destination 1 light-year away in a specific direction with a position accuracy of better than a few million kilometers, requires extremely accurate knowledge of the spacecraft's initial trajectory and velocity. Any small error in the launch velocity that goes uncorrected will accumulate over the multi-decade transit into a positional error proportional to the velocity error times the transit time. A velocity error of 1 meter per second, tiny by current standards for spacecraft tracking, accumulated over 40 years of transit produces a positional error of roughly 1.26 billion kilometers, or about 8.5 astronomical units. This is a large error by interstellar navigation standards. Laser ranging from Earth, in which a laser pulse is sent to the spacecraft and the return reflection is timed, provides precise distance measurement if the spacecraft carries a retroreflector. But at 1 light-year, the 2-year round-trip time means any ranging measurement is 2 years old when it is received, and the spacecraft has moved substantially in the intervening time. Active navigation corrections using spacecraft maneuvers are possible in principle but require propellant that may be budgeted tightly for other purposes. The practical solution likely involves a combination of initial trajectory precision at launch, periodic autonomous celestial navigation using stars and pulsars, and occasional correction burns if the trajectory has drifted enough to threaten mission success. The pulsar timing network, which has been developed for fundamental physics experiments, could provide absolute position references with uncertainties of a few kilometers throughout interstellar space if the onboard instruments are sufficiently precise, making it the most promising autonomous navigation technique for interstellar missions. The absence of GPS at interstellar distances is worth stating plainly. GPS works because signals from multiple satellites at known positions, broadcasting precisely synchronized time signals, allow a receiver to compute its position by measuring the delay of each signal. At interstellar distances, there are no satellites, no synchronized network, and the signals from any home-based transmitter arrive with 1-year-plus delays that make real-time positioning impossible. The navigation challenge at interstellar distances is therefore not a matter of improving GPS coverage but of developing fundamentally different positioning methodologies that work without any real-time communication with the origin point. At 1 light-year, you have not left the solar system in any conventional sense. You are within the estimated extent of the Oort Cloud, the vast, roughly spherical shell of icy bodies that surrounds the solar system at distances ranging from perhaps 2,000 to 100,000 astronomical units, or roughly 0.03 to 1.6 light-years. 1 light-year lies squarely within this region, and understanding what the Oort Cloud is and what it contains is part of understanding what awaits a traveler at that distance. The Oort Cloud is a theoretical construct in the sense that no individual Oort Cloud object has been directly observed in situ. What gives us confidence in its existence is the orbital behavior of long-period comets, those comets with orbital periods greater than 200 years that appear in the inner solar system for the first time on highly elliptical orbits coming from all directions in three-dimensional space. The isotropy of these cometary orbits indicates a spherical source reservoir rather than a flattened disk structure like the Kuiper belt. Calculating backward along the observed orbits of these comets indicates aphelion distances typically in the range of thousands to hundreds of thousands of astronomical units, consistent with the Oort Cloud model first proposed by Jan Oort in 1950. The total mass of the Oort Cloud is estimated at somewhere between 1 and several Earth masses, distributed across a vast volume of space in objects that range from small icy grains to comet nuclei tens of kilometers across. The number density of objects in the Oort Cloud is extraordinarily low. Estimates suggest perhaps 10 to the 12 to 10 to the 13 objects with diameters above a kilometer, distributed through a volume of space roughly 40 trillion cubic astronomical units. The average spacing between Oort Cloud objects is on the order of tens of millions of kilometers. A spacecraft navigating through the Oort Cloud would be in no danger of collision with these objects. The cloud is extraordinarily sparse by any practical measure, and the probability of passing within even 1 million kilometers of any single object is negligibly small over any realistic trajectory. The Oort Cloud is not a dense shell that must be threaded but an almost entirely empty space in which a few objects are very widely scattered. What the Oort Cloud does represent is the gravitational domain of the Sun, the region in which objects are bound to the Sun's gravity rather than to the gravitational field of the galaxy or of neighboring star systems. The outer boundary of the Oort Cloud marks approximately where the Sun's gravity becomes too weak to hold objects against the tidal perturbation of the galactic disk, and is therefore a rough definition of the solar system's gravitational sphere of influence. Long-period comets provide the primary observational evidence for the Oort Cloud's existence, but they also reveal something about the dynamics that populates the Oort Cloud in the first place. The Standard Model proposes that the Oort Cloud was populated in the early solar system by objects that formed in the giant planet region and were gravitationally scattered outward by encounters with Jupiter, Saturn, Uranus, and Neptune. The scattered objects reached the outer solar system with enough energy to be on highly elliptical orbits but not quite enough to escape the solar system entirely. The galactic tide, the differential gravitational force from the Milky Way's disk and bulge acting across the large spatial extent of the distant solar system, then slowly raised the perihelia of these scattered objects, lifting their closest approaches to the Sun above the planet's scattered region and into the stable Oort Cloud. This dynamical history means the Oort Cloud is not a relic structure from the solar system's formation but a dynamically evolved structure that has been continuously modified by the galactic environment and by passing stars and molecular clouds. The current Oort Cloud population is estimated to have been significantly depleted from its peak by close stellar encounters over the solar system's history, with some estimates suggesting the initial Oort Cloud was 10 to 100 times more massive than the current population. For a spacecraft transiting through the Oort Cloud, the dynamical significance of this region is that it is the last domain where the Sun's gravity definitively dominates the dynamics. Beyond the Oort Cloud's outer edge, the galactic tide and the gravity of neighboring stars begin to become as significant as the Sun's gravity in determining the trajectories of small objects. A spacecraft that ran out of fuel in the Oort Cloud would slowly drift in an orbit around the Sun, potentially for billions of years. A spacecraft that ran out of fuel beyond the Oort Cloud would drift through interstellar space forever. Before reaching the Oort Cloud, any spacecraft leaving the solar system must pass through a series of physical boundaries that mark the transition from the Sun-dominated environment of the inner solar system to the interstellar medium. The most significant of these boundaries for spacecraft operations is the heliopause, which Voyager 1 crossed in August 2012, making it the first human-made object to enter interstellar space. The heliosphere is the region of space dominated by the solar wind, a continuous stream of charged particles, primarily protons and electrons, flowing outward from the Sun at speeds of 400 to 800 kilometers per second. The solar wind carries with it the Sun's magnetic field, and together the wind and field maintain a bubble of solar influence against the pressure of the interstellar medium. The boundary where the solar wind pressure and the interstellar medium pressure are in equilibrium is the heliopause. The structure of the heliosphere is more complex than a simple sphere. As the solar system moves through the interstellar medium at roughly 25 kilometers per second, the heliosphere is compressed in the direction of travel and elongated in the opposite direction. The Voyager measurements found the heliopause at about 121 astronomical units in the direction Voyager was traveling, consistent with theoretical predictions. The nose of the heliosphere, in the direction of solar motion, is estimated to be closer, perhaps at 100 astronomical units. Beyond the heliopause, the environment changes in several measurable ways. The particle environment transitions from solar wind particles to galactic cosmic rays. The magnetic field transitions from the Sun's outward-flowing spiral field to the more complex interstellar magnetic field, which in the local region has a specific orientation that Voyager's instruments have measured. The plasma density changes from the solar wind's low-density, high-temperature plasma to the denser, lower-temperature interstellar plasma. The consequences for a spacecraft crossing the heliopause include a significant increase in radiation exposure. Inside the heliosphere, the solar wind provides some modulation of galactic cosmic rays, reducing the flux of the most damaging particles. Outside, this modulation disappears and the full interstellar cosmic ray environment is present. Voyager's instruments detected a sharp increase in cosmic ray flux coincident with crossing the heliopause, confirming the shielding effect of the heliosphere. The Voyager 1 crossing of the heliopause provided the first in situ measurements of conditions in the very local interstellar medium. The spacecraft's plasma wave instrument detected oscillations that allowed the plasma density just outside the heliopause to be estimated at roughly 0.08 electrons per cubic centimeter, consistent with models of the warm ionized component of the local interstellar medium. The magnetic field direction outside the heliopause, measured by Voyager's magnetometer, was found to be at an angle of roughly 40 degrees to the direction predicted by optical polarization measurements of nearby stars, suggesting that the local interstellar magnetic field has a complex structure in the immediate solar neighborhood. The transition across the heliopause was not a single sharp boundary but a region of turbulent mixing. Voyager's instruments detected multiple encounters with what may be the boundary over a period of months before the transition appeared to be definitively complete. The actual physical boundary between the heliosphere and the interstellar medium may be more complex than a simple surface, involving instabilities and mixing layers driven by the differential flow between the solar wind and the interstellar medium. Importantly, Voyager 1 continues to function and transmit data more than 12 years after crossing the heliopause. This is both a testament to the spacecraft's engineering and a demonstration that surviving the crossing itself is not the primary challenge. The challenge is that the spacecraft is moving too slowly to reach any destination of scientific interest in any reasonable time frame, and it lacks the capability to collect the interstellar medium samples, image the local stellar environment, or perform most of the scientific measurements that would make an interstellar mission scientifically productive. The distance at which the heliopause lies is not fixed. The solar wind pressure varies with the solar cycle, with solar maximum producing higher pressure than solar minimum, and this variation causes the heliopause to move inward and outward by perhaps a few astronomical units over the 11-year solar cycle. Stellar encounters in the past may have significantly distorted the heliopause shape and moved it substantially. In the direction of the solar system's motion through the interstellar medium, the heliosphere is compressed. In the opposite direction, it is extended in a long heliotail that Voyager 1 is not traveling through. The actual distance to the heliopause depends strongly on direction. Given that chemical rockets are essentially useless for interstellar travel on any relevant timescale, and that nuclear pulse propulsion offers dramatic improvements but is still limited by the rocket equation's requirement to carry reaction mass, several alternative propulsion concepts have been studied in detail. Understanding their specific capabilities and limitations is essential for assessing what traveling 1 light-year might actually look like. The fusion rocket represents the most commonly discussed high-performance chemical analog propulsion concept. By fusing deuterium and tritium, or deuterium and helium-3, a fusion rocket could in principle achieve specific impulse values corresponding to exhaust velocities of several to tens of % of the speed of light. This would make the mass ratio requirements for interstellar missions manageable. A mass ratio of 5 to 10 would provide sufficient delta-v for one-way interstellar missions at 10 to 20% of light speed. The catch is that sustained thermonuclear fusion has not been achieved in any practical form even for terrestrial power generation, let alone in the compact, efficient, thrust-producing form required for a rocket engine. The Bussard ramjet, proposed by Robert Bussard in 1960, attempted to sidestep the rocket equation entirely by collecting interstellar hydrogen as it flew through it and using this hydrogen as both fuel and reaction mass. The magnetic scoop needed to collect hydrogen over a sufficient area would need to have a radius of many kilometers, and subsequent analysis showed that the drag from the magnetic field on the interstellar medium would likely exceed the thrust from burning the collected hydrogen at achievable densities in the local interstellar medium. The ramjet remains a fascinating concept but appears not to be viable. The laser sail concept, explored seriously by Jeffrey Landis and the Breakthrough Starshot Initiative, uses a powerful ground-based laser to push a lightweight reflective sail without requiring the spacecraft to carry any propellant at all. The fundamental constraint becomes the laser beam power and focusing rather than the rocket equation. Breakthrough Starshot proposes using a laser array producing roughly 100 gigawatts to accelerate a gram-scale spacecraft to 20% of light speed in a few minutes. For such a spacecraft to reach 1 light-year, the laser must continue illuminating the sail for several minutes as it accelerates, and the beam must remain focused on the sail despite diffraction spreading over the increasing distance. The solar sail is a related concept that replaces laser photons with sunlight. Solar sails accelerate using the radiation pressure of sunlight, which provides a force proportional to the sail area and inversely proportional to the square of the distance from the Sun. JAXA's Icaros mission, launched in 2010, demonstrated solar sail propulsion in interplanetary space, and the Planetary Society's Light Sail 2 demonstrated attitude control using sail orientation. The fundamental limitation of solar sails for interstellar travel is that the available force decreases with distance from the Sun, falling to negligible levels by the time the spacecraft reaches a few astronomical units. Solar sails can accelerate a spacecraft to modest velocities in the inner solar system but cannot sustain that acceleration through the journey to another star. The magnetoplasma sail concept uses a magnetic field rather than a physical sail to interact with the solar wind for propulsion. By generating a large magnetic field around the spacecraft, the solar wind's charged particles can be deflected, producing thrust. The advantage over solar sails is that the magnetic field can, in principle, be generated by an active electromagnetic coil rather than requiring a physical sail structure, allowing very large effective capture areas without corresponding mass. The magnetoplasma sail faces the same fundamental limitation as the solar sail. The solar wind density and pressure decrease with distance from the Sun, making it ineffective for the vast majority of an interstellar journey. Nuclear electric propulsion, in which a nuclear reactor provides electrical power to accelerate ions to high exhaust velocities, combines the energy density advantage of nuclear power with the efficiency advantage of ion drives. Current ion thrusters achieve exhaust velocities of 30 to 80 km per second, and nuclear electric systems could potentially push these toward 200 km per second or beyond. This is vastly better than chemical rockets but still subject to the rocket equation, limiting achievable velocities to somewhat below the exhaust velocity for practical mass ratios. The Project Longshot concept, a study conducted in part at the U.S. Naval Academy in 1987 and 1988, proposed a crewed mission to Alpha Centauri using a fission-fusion hybrid pulse propulsion system, similar in concept to Project Daedalus but with different design parameters. The study estimated a transit time of approximately 100 years with a spacecraft mass at departure of about 396,000 kilograms, of which about 264,000 kilograms would be propellant. The study identified several unsolved engineering problems, including the need for a power system with no maintenance requirements operating for a century, and acknowledged that the propulsion technology it proposed did not yet exist in any experimental form. The most persistently underemphasized problem in discussions of interstellar travel is deceleration. Popular discussions of reaching other stars tend to focus on acceleration, on how to get a spacecraft up to a significant fraction of light speed. The problem of slowing down is at least equally severe and in many ways more difficult, because the techniques that might solve the acceleration problem do not necessarily have a deceleration equivalent. For any rocket-based propulsion system, the fuel required for deceleration is at least as much as the fuel required for acceleration by symmetry. If you need to carry enough fuel to accelerate to 10% of light speed, you need to carry enough to decelerate by 10% of light speed at the end of the journey. But the fuel for deceleration must be carried along for the entire acceleration phase, which means the initial mass at launch must include the fuel for deceleration, the fuel needed to accelerate the deceleration fuel, the fuel needed to accelerate the fuel that accelerates the deceleration fuel, and so on in the exponential regress of the rocket equation. For the laser sail concept, this problem is particularly acute. The laser pushes the sail in the direction of travel, but there is no way to use the same laser to slow down. By the time the spacecraft needs to decelerate, it has traveled 1 or more light years from the laser array, and the distance makes the beam diverge and weaken to the point of irrelevance. Various proposals for laser sail deceleration include detaching part of the sail, which remains behind to reflect the laser beam forward, using the beam to push a subsail against the direction of travel, using the stellar wind or magnetic field of the destination star for magnetic braking, and using a laser at the destination, which requires someone to have placed a laser array at the destination beforehand, which requires an initial slower mission to establish the infrastructure. The deceleration problem is the reason that a one-way flyby mission to a nearby star requires only half the propellant of a stop-and-return mission, and it is the reason that breakthrough Starshot's gram-scale sailcraft are explicitly designed as flyby probes rather than orbiters or landers. They will pass through the Alpha Centauri system at 20% of light speed, taking pictures and measurements for a few hours as they fly by, with no capability to stop or return. The magnetic braking concept for deceleration at the destination is one of the more elegant proposed solutions. If the destination star has a stellar wind analogous to the solar wind, a spacecraft carrying a superconducting coil could deploy a large magnetic field on arrival, using the interaction between the coil's field and the flowing stellar wind to provide a braking force. The effectiveness of this approach depends on the density and speed of the destination star's stellar wind and on the size of the magnetic field that can be practically deployed. For Proxima Centauri, which is an active flare star with a stronger than average stellar wind, magnetic braking might provide significant deceleration at relatively low engineering cost. The laser braking variant of the laser sail concept involves separating the sail into two components near the destination: a smaller central sail carrying the payload and a larger outer ring sail that remains between the laser at the origin and the inner sail. The outer sail reflects the incoming laser beam back toward the inner sail, creating a forward force on the inner sail relative to the destination, which acts as braking. This approach requires precise manufacturing of the sail components and careful management of the relative positions of the two sails during the deceleration phase, but it uses the same laser infrastructure as the acceleration phase and avoids the need for a separate propellant supply for deceleration. For any crewed mission, the deceleration problem is not optional. A spacecraft that arrives at the destination at 20% of the speed of light and cannot decelerate will pass through any stellar system in a matter of days and continue into the interstellar medium in the other direction. The crew would have a brief window to conduct observations before losing the destination, and the mission would effectively be a flyby rather than an arrival. This is why the deceleration problem must be solved before human interstellar travel can be considered viable, not just difficult. The Matloff dark mass gravitational lens concept deserves mention for its ingenuity even if its practicality is questionable. Astrophysicist Gregory Matloff proposed that a spacecraft approaching a stellar system could use the gravitational field of the destination star as a braking mechanism by flying a trajectory that curves around the star at a close distance, using the gravitational interaction to redirect the spacecraft's velocity rather than simply slowing it. This concept, analogous to the gravity assist maneuvers used in solar system missions but used for deceleration rather than acceleration, avoids the need for propellant at the destination. Whether the trajectory geometry required for meaningful deceleration in a single stellar encounter is achievable at the approach velocities relevant to interstellar missions is a matter of ongoing analysis. At the velocities that any realistically near-future propulsion system could achieve, a 1 light-year journey would take between several decades and tens of thousands of years. The specific transit time determines the character of the life support challenge, but in all cases the challenge is genuinely extreme. For a journey lasting decades, the life support requirements are analogous to but more demanding than the longest human space missions attempted to date. The longest continuous human spaceflight was Valery Polyakov's 437-day mission on the Mir space station in 1994 to 1995. ISS astronauts routinely serve 6-month tours, with some 12-month missions, and the longest cumulative time any human has spent in space is currently held by Oleg Kononenko at over 800 days. These missions reveal the specific physiological effects of long-duration spaceflight, most of which are driven by the absence of gravity and the elevated radiation environment. Microgravity produces bone density loss of roughly 1 to 2% per month in weight-bearing bones if countermeasures are not applied. Muscle mass declines. Fluid redistribution from the lower body to the upper body and head causes visual impairment in a significant fraction of astronauts, a condition called spaceflight-associated neuroocular syndrome whose long-term consequences are still being assessed. Cardiovascular deconditioning occurs as the heart adapts to the reduced requirement for pumping blood upward against gravity. The immune system shows changes that could increase vulnerability to infection during long missions. Providing artificial gravity through rotation is the standard proposed solution to most microgravity health effects. A rotating habitat provides a centrifugal acceleration that serves functionally as gravity, with the effective gravity at the outer edge of the habitat proportional to the rotation rate and the radius. At a 1 gravity equivalent, the biological effects of microgravity would largely be avoided, at the cost of engineering complexity. The rotation rate must be low enough to avoid vestibular disturbance, typically below about 2 revolutions per minute, which at standard gravity requires a rotation radius of at least 224 meters. This is a large structure by any current spacecraft standard. Water is the most massive consumable per person per day, and recycling it to near completeness is essential for any long-duration space mission. The water recovery system on the International Space Station recovers approximately 93% of crew water from humidity condensate and urine, reducing the amount that must be supplied from Earth. For an interstellar mission with no possibility of resupply, even 93% recovery would result in significant cumulative losses over decades of transit. A crew of 6 losing 7% of their water per cycle would lose more than half their water supply in about 10 years without any resupply mechanism. Achieving recovery efficiencies above 99% is a technical goal for long-duration spaceflight that has not yet been demonstrated at operational scale. Food presents similar challenges. Current ISS food is entirely prepackaged and launched from Earth. Growing food on the space station has been demonstrated at small scales, but the station has never been food self-sufficient. For a multi-decade interstellar mission, some degree of food production on board would be essential both for caloric needs and for the psychological benefits of having living organisms and a connection to biological cycles aboard. Closed-loop agriculture in the constraints of a spacecraft requires managing light, water, nutrients, and atmosphere in a system that is simultaneously productive enough to provide meaningful food production and compact enough to fit within the spacecraft's volume and mass budget. The failure modes of life support systems in the context of an interstellar mission are more severe than in any previous human spaceflight context. On the ISS or on a proposed Mars mission, A life support failure that cannot be resolved in days to weeks can be addressed by emergency return to Earth or by resupply from Earth within months. At 1 light year, Earth cannot help in any timescale relevant to the emergency. The spacecraft's life support systems must therefore either be essentially fail-safe or must carry sufficient redundancy and repair capacity to address any single-point failure indefinitely. The atmosphere management problem, maintaining a breathable mix of oxygen and nitrogen or oxygen and argon at appropriate pressure and humidity while removing carbon dioxide produced by the crew's metabolic processes, requires continuous operation of chemical or biological systems for the entire duration of the mission. The ISS uses lithium hydroxide canisters and a molecular sieve to remove carbon dioxide and a series of electrolytic systems to regenerate oxygen from water. These systems have performed reliably over years of ISS operation, but they require periodic replacement of consumable components and maintenance. For a multi-decade interstellar mission, the mean time between failures of every component must exceed the mission duration, or the crew must carry sufficient spare parts and repair capability to address any failure, including failures of the repair equipment itself. The physiological challenges of long-duration spaceflight are well documented in the literature from ISS missions and from the psychological studies conducted by NASA, ESA, and other agencies. The psychological challenges are in some respects more difficult to anticipate and to prepare for, because they involve the specific context of isolation, confinement, and the loss of normal social and cultural connections, in a manner unprecedented in the history of human experience. Antarctica provides the closest terrestrial analog to long-duration spaceflight isolation. Research stations like the Amundsen Scott South Pole Station maintain crews of several dozen people through the winter-over period of roughly 8 months during which no aircraft can reach or leave the station and the crew is completely isolated from the outside world. The psychological effects documented in winter-over crews include what researchers call the third-quarter phenomenon, a psychological downturn in morale and performance that tends to occur in the third quarter of the isolation period, as well as interpersonal conflicts, cognitive performance decrements, and in some cases neuropsychiatric symptoms ranging from depression to psychotic episodes. For an interstellar voyage lasting decades, the psychological challenges would be qualitatively different from any previous human experience. A crew would need to maintain coherence and productive collaboration not just for months but for the entirety of their adult lives. The Earth they left would be represented only by old recordings and memories, with any real-time connection impossible due to the multi-year communication delay. The destination would be visible only as a slowly brightening star for most of the journey, with no feedback from arrival until the journey's completion. The crew would need to be self-sufficient in every meaningful sense, not just physically but socially and culturally. They would need to make all decisions independently, including medical decisions, engineering decisions and social decisions, without the possibility of real-time consultation with experts on Earth. They would age aboard the ship. Some might die before arrival if the journey lasted multiple decades. Children born aboard would have no experience of any planetary surface until they arrived at the destination, if at all. The confinement of a spacecraft environment adds to the psychological stress of isolation. ISS crew members have access to windows looking out on Earth, which provides a continuous visual connection to home and to the scale of the planet. They receive fresh food packages, personal messages, news updates and video calls with family several times per week. They have a continuous sense of connection to humanity even in their extreme physical isolation. An interstellar crew would have none of these connections. Communication with Earth would have a minimum 2-year delay, making real-time interaction impossible. Any personal messages would be pre-recorded. Any news from Earth would be 2 or more years old by the time it arrived. The spacecraft's windows would show a sky in which the sun is just one star among many, growing fainter year by year. The crew would have no visual connection to Earth, no daily news cycle, no sense of participating in the life of the civilization that sent them. The design of social structure for an interstellar crew is a serious research question that has received relatively little attention. On ISS missions, crew members are selected partly for psychological stability and interpersonal compatibility, trained extensively in conflict resolution, and supported by a large team of psychologists on the ground. For an interstellar mission, the crew would need to function as a largely self-governing community for their entire working lives. The governance structures, conflict resolution mechanisms, and social contracts that would allow a small isolated group to maintain productive functioning over decades without external support have no precedent in human experience and would need to be developed from scratch. Assuming the impossible, the propulsion, the life support, the radiation shielding, and the navigation have all been solved, and a spacecraft arrives at a distance of approximately 1 light-year from Earth. What is there? What has all this effort brought you to? At 1 light-year, in the direction of the nearest known star systems, you are in the outer Oort cloud of the solar system. There are no other significant gravitational structures in this direction. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. You have covered roughly a quarter of the distance to the nearest star. The Alpha Centauri triple system at the same direction is slightly farther. You are surrounded by the same sparse interstellar medium that pervades the region between the solar system and neighboring stars, with a hydrogen density of roughly a fraction of an atom per cubic centimeter. From 1 light-year, the Sun would appear as a star of apparent magnitude approximately -9, dramatically brighter than any star visible from Earth with the naked eye, which means any star brighter than magnitude 6. The Sun at this distance would be roughly as bright as a crescent moon viewed from Earth, a brilliant point of light but not a disk. The solar system's planets would be completely invisible. Earth would be detectable only with a telescope of extraordinary capability, and its detection would require the same technique proposed by Carl Sagan for locating Earth-type planets around other stars, watching for the tiny periodic dimming of the Sun as Earth transits across its face. Proxima Centauri would be 3.24 light-years away, still very faint and unresolved. Visible stars would appear distributed across the sky in the same patterns as seen from Earth, with only modest shifts in the positions of the nearest stars due to the changed parallax baseline. The Milky Way band would appear essentially identical to its appearance from Earth. The constellations would be recognizable, though stars closer than about 100 light-years would have shifted positions by a few arc-minutes or more. What you would have accomplished is reaching the outer boundary of the solar system's gravitational sphere of influence, crossing into the genuine interstellar medium, surviving the radiation and dust environment of that crossing, and demonstrating that the physical and engineering problems of interstellar travel are manageable at this scale. It would be perhaps the most significant achievement in human history. It would not be the discovery of another world. The view of the Milky Way from 1 light-year would be essentially indistinguishable from the view from Earth with the naked eye, because the change in viewing position is negligible compared to the scale of the galaxy. Instrument measurements would show small but detectable changes in the distances to nearby stars, with parallax shifts measurable at the arc-second to subarc-second level for the nearest examples. The interstellar magnetic field, measured directly by onboard instruments, would have a specific orientation and strength in this region of the local interstellar cloud that would differ from measurements made inside the heliosphere. The scientific value of a spacecraft at 1 light-year, even in the apparently featureless void of the outer Oort cloud, would be significant. Very long baseline interferometry baselines of 63,241 astronomical units, compared to the current maximum baselines of the Earth-Moon system at less than 1.5 astronomical units, would provide angular resolutions millions of times sharper than current Earth-based VLBI. At radio wavelengths, features of astrophysical sources could be resolved that are currently impossible to distinguish. The imaging resolution for the black hole in M87 at this baseline would be comparable to resolving structures the size of Earth at M87's distance, instead of the current limit, which is comparable to resolving structures the size of the solar system. The spacecraft would also be ideally placed to measure the three-dimensional interstellar magnetic field by comparing its measurements to those of both Earth-based observatories and Voyager's measurements at a different location and distance. The cosmic ray environment, the interstellar gas density, the dust distribution, and the heliospheric tail, the elongated downwind extension of the heliosphere caused by the Sun's motion through the interstellar medium, would all be observable from this position in ways impossible from within the solar system. The question of what the sky looks like from 1 light-year provides one more concrete image for what the journey would involve. The Sun, seen from 1 light-year, has an apparent magnitude of roughly -9.5. For comparison, the full Moon has an apparent magnitude of about -12.9, Sirius has an apparent magnitude of -1.4, and Venus at its brightest is about -4.9. The Sun from 1 light-year would be much brighter than any normal star visible from Earth, more similar in brightness to Venus near greatest elongation or to a crescent moon, but concentrated to a point source rather than a disk. It would be invisible by day if there were a day, but in the permanent space night of the journey, it would be the brightest object in the sky by a factor of several hundred over the next brightest stars. Every serious analysis of interstellar propulsion converges on the same conclusion. The energy required to accelerate a meaningful payload to a meaningful fraction of light speed is staggering by any comparison to current energy production. Understanding the specific numbers is essential for understanding both why this is so difficult and what future energy sources would be needed to make it possible. The kinetic energy of an object with mass m moving at velocity v, in the relativistic case, is given by the gamma factor minus 1 times mc squared. For a 1,000 kilogram spacecraft, roughly the mass of a modest unmanned satellite, accelerated to 10% of the speed of light, this kinetic energy is approximately 4.5 times 10 to the 17th joules, or roughly 450 petajoules. Global annual energy consumption in 2023 was approximately 620 exajoules, or 6.2 times 10 to the 20 joules. Propelling a 1-ton spacecraft to 10% of light speed would therefore require about 0.07% of current annual global energy consumption, dedicated entirely to this single propulsive effort. But this is the kinetic energy of the payload alone. If the spacecraft is propelled by rockets and must carry its own fuel, the initial mass is much larger than the final payload mass, and the energy must accelerate the fuel as well as the payload. For a fusion rocket with an exhaust velocity of 10% of light speed and an initial mass ratio of 10, meaning 9/10 of the initial mass is propellant, the energy required to drive the entire system is approximately 10 times the kinetic energy of the payload, or roughly 4.5 times 10 to the 18 joules, comparable to the world's current annual energy production. For a laser sail system that avoids the rocket equation by using a ground-based laser, the energy in the beam is more efficiently converted to spacecraft kinetic energy, but the quantities are still substantial. Breakthrough Starshot's proposed 100-gigawatt laser array, running for several minutes to accelerate a gram-scale craft to 20% of light speed, requires an energy input of roughly 10 to the 15 joules per craft. For a human-carrying mission with a 1,000-kilogram spacecraft at 20% of light speed, the energy would be roughly 1,000 trillion times larger, or approximately 10 to the 27 joules, which is about 10 million times the current annual global energy production. The comparison with specific real-world energy producers is worth making concrete. A nuclear power plant producing 1 gigawatt of electrical power continuously for 1 year produces about 31.5 petajoules of electrical energy. The energy required to accelerate a 1-ton spacecraft to 10% of light speed is approximately 450 petajoules, equivalent to about 14 gigawatt years, or the output of a single gigawatt power plant for 14 years. This sounds almost manageable, and it would be if the energy could be perfectly converted to spacecraft kinetic energy. The problem is that no propulsion system converts energy to kinetic energy with 100% efficiency, and the rocket equation means most of the energy must be used to accelerate propellant rather than payload. For a fusion rocket with 50% efficiency at producing thrust from fusion energy, and a mass ratio of 10, the actual fusion energy consumed would be roughly 10 times the payload kinetic energy divided by the efficiency, or about 90,000 petajoules, equivalent to approximately 3,000 gigawatt years of nuclear power, or the combined output of 3,000 large nuclear power plants running for a year. This is the entire current nuclear power generating capacity of Earth operated continuously for about 2.5 years, dedicated entirely to powering one interstellar mission. This analysis makes the energy cost of interstellar propulsion concrete. It is not physically impossible in terms of the energy available, because the Sun produces about 3 times 10 to the 26th watts, roughly a million times humanity's current energy consumption. But it is wildly beyond anything that current civilization can deploy for any single purpose. The transition from current energy consumption to the energy scales required for interstellar propulsion requires either a fundamental change in human civilization's energy infrastructure or the development of propulsion methods, like the laser sail, that move the energy production requirement from aboard the spacecraft to a stationary installation. The difficulties of traveling 1 light year, while individually daunting and collectively almost paralyzing from the perspective of current civilization, should not obscure what the achievement would mean if accomplished. Understanding the magnitude of what reaching 1 light year would represent is part of understanding why, despite all the difficulty, the question is worth taking seriously. No robotic mission has yet left the solar system with a specific destination and arrival plan. Voyager 1 is in interstellar space but was not aimed at any star and will not approach another star for over 40,000 years. A mission that successfully crossed 1 light year with a functional spacecraft, even unmanned, would represent the first intentional transit from one point in interstellar space to another, the first use of technology to close a distance that has previously been unbridgeable in any direction. The scientific return from such a mission would be enormous. A spacecraft at 1 light-year would have baselines for very long baseline interferometry observations of astrophysical sources that are 63,000 times longer than any baseline available within the solar system, enabling angular resolutions in radio astronomy that would revolutionize the imaging of distant structures. It would measure the cosmic ray environment, the interstellar magnetic field, the gas and dust density, and the photometric environment of the outer Oort cloud from within, rather than inferring these properties from remote sensing. A crewed mission that successfully reached 1 light-year and returned would represent the most significant expansion of the human physical domain in history. Every previous expansion, from Africa to the rest of Earth, from Earth to the Moon, from the Moon to Mars in any hypothetical future, involved crossing distances that pale compared to even a single light-year. The psychological and cultural impact of knowing that human beings had physically stood in interstellar space, had looked back at the solar system as a single bright point, and had returned, would be comparable in magnitude to no previous human achievement. The technologies required to reach 1 light-year, whatever their ultimate form, would be transformative for all other aspects of human civilization. The energy production capable of powering an interstellar propulsion system would also power everything else. The radiation shielding and life support systems capable of sustaining humans through interstellar space would also be capable of sustaining long-duration bases anywhere in the solar system. The navigational technology and communication systems required at 1 light-year would also serve in ways no current technology can. The trajectory of human exploration, viewed broadly, has always involved extensions of reach that required overcoming specific technical barriers that seemed at the time to be near absolute. The barriers to ocean navigation, to polar exploration, to aviation, to spaceflight, were each in their historical context described as essentially insurmountable by cautious thinkers, and in each case the description was simultaneously accurate about the difficulty and wrong about the impossibility. The barriers to reaching 1 light-year are real, quantifiable, and far more severe than any previous barrier in the history of human exploration. But the history provides some reason for humility about predictions of impossibility. The interstellar medium at 1 light-year is not the most interesting place in the universe. It is not a destination that contains anything obviously worth going to. What it represents is a proof of concept, a demonstration that human technology and human will can bridge distances that currently seem unbridgeable. This is what drove the first ocean crossings, which ended at coasts that had been inhabited for thousands of years and contained nothing that was not already available elsewhere. The demonstration that the crossing could be done, and the infrastructure and knowledge developed in making it possible, was the real achievement. An interstellar-capable civilization would be, by any measure, a more robust civilization than one confined to a single solar system. The physical separation of populations at interstellar distances makes catastrophic risks, asteroid impacts, solar events, geopolitical catastrophes, unable to affect all of humanity simultaneously. The development of technologies capable of sustaining human life on interstellar voyages would also provide the capability to sustain human life in essentially any environment within the solar system. 1 light-year is a distance that puts the human situation in perspective more efficiently than almost any other single astronomical quantity. It is close enough to feel in principle reachable, close enough that we can draw a straight line from current technology to some hypothetical future technology and imagine the gap being crossed. It is far enough that the gap requires crossing every significant barrier in energy production, materials science, radiation biology, life support, navigation, and propulsion simultaneously, and solving problems that have no precedent in the history of engineering. What we learn from taking the question seriously, from following through on what would actually happen physically at every scale and in every domain, is not despair but precise calibration. The barriers are not vague and insurmountable. They are specific and in most cases quantifiable. The rocket equation demands specific mass ratios that specific exhaust velocities can satisfy. The radiation environment delivers specific doses that specific shielding configurations can reduce. The dust impact problem requires specific shield materials that specific material science can address. The time dilation of relativistic travel is calculated by specific equations that specific velocities produce specific results from. The psychology of isolation is studied in specific populations under specific conditions with specific outcomes that specific mission design parameters can influence. Taking the question of 1 light-year seriously forces precision where vagueness would be comfortable. It forces acknowledgement of the specific distances involved, the specific physics that governs them, and the specific gap between current capability and what would be needed. That precision is valuable not as a counsel of impossibility but as a map of what specifically needs to be achieved. The universe is in some sense designed to make interstellar travel hard. The speed of light is finite and nothing informational can travel faster. The rocket equation is exponential and cannot be repealed. The radiation environment between stars is genuinely hostile and cannot be negotiated with. These facts are not arguments against attempting the journey. They are arguments for taking the journey seriously enough to understand what it actually requires, so that any effort directed toward it is directed at real problems rather than imaginary ones. The distance of 1 light-year is simultaneously an indictment of current capability and an invitation to think seriously about what it would take to cross it. No one alive today will make that crossing. Possibly no one in the next several generations will. But the question of what would actually happen if you traveled 1 light-year is one of the most productive questions you can ask about the future of the species, because the answer is a precise statement of what would need to be true for the answer to become possible. And understanding what would need to be true is the first step in the direction of making it so. There is also something philosophically significant about the specific distance of 1 light-year. It is not determined by any astrophysical feature like a star's location or a planet's orbit. It is determined by the intersection of 2 human measures, the duration of the year and the speed of light, and it represents the unit of cosmic distance that has proven most useful for describing the scale of stellar separations. Asking what would happen in crossing 1 light-year is therefore asking what the universe is actually like at the scale that separates stars, what the texture of interstellar space is, what the physics imposes on any attempt to close that gap. The universe's answer to this question is complex and specific. It involves the exponential cruelty of the rocket equation, the radiation field of galactic cosmic rays, the kinetic violence of interstellar dust at high speed, the relativistic transformation of light into blue-shifted radiation from ahead, the 2-year communication silence, the autonomous navigation requirements, and the multi-decade life support and psychological demands of isolation. None of these are metaphorical difficulties. They are physical facts, each one precisely quantifiable, each one the subject of ongoing scientific and engineering investigation. What would actually happen if you traveled 1 light-year depends on how you traveled. At current speeds, nothing would happen because you would never arrive in any relevant sense. The journey would take longer than civilization has existed, and whatever you sent would be a relic before it covered a fraction of the distance. At a significant fraction of light speed, achievable only through technologies not yet demonstrated but not prohibited by known physics, what would happen would be extraordinary in ways both expected and unanticipated. The relativistic transformation of the visual world, the 2-year silence of communication, the crossing from the heliosphere into interstellar space, the gradual dimming of the sun into just another star, and eventually the arrival at a location where you had placed yourself. Genuinely between the stars, in the oldest and deepest emptiness accessible to human experience. The honest answer to the question is that we do not know exactly what would happen because we have never done it and cannot do it yet. But we know with considerable precision what the physics requires, what the obstacles are, and what achieving it would mean. That knowledge is not nothing. In the history of human exploration, knowing what a journey actually requires has always been the prerequisite for eventually making it.